Hello students, this is Mr. Hart, and in this video we want to continue looking at algorithms and have some more practice with them, and we also want to solve the elevator problem that we looked at last time. Okay, so just as a reminder, an algorithm is a process or set of rules that we follow in order to complete a calculation. So in the elevator problem, for example, the input was the number of floors that people needed to travel. We need to solve and figure out the best way to send them up the elevator to get the least number of floors traveled. Okay, so given some input, what do I need to do to get the desired result? Okay, so that's the algorithm that we want to follow, right? We need to figure out. A side note I want to make really quick that I forgot to mention last time is there's a lot of ways you can make algorithms. Okay, I put a video on Canvas that was pretty funny going over the way people make peanut butter and jelly sandwiches. Studio C does a funny video on this. Everyone has a way they like to make a PB&J sandwich. Just like there's different ways you can complete tasks, there's different algorithms you can use to complete certain tasks. Okay? Sometimes algorithms are better than others, and so that's what we want to discuss as well. Sometimes there is a best way to complete a task, but sometimes it's just a matter of opinion, and there's multiple ways a thing can be done. Okay? So let's go ahead and look at the elevator problem. This one does happen to have a best algorithm, and that's what we want to go through right now. Okay, so just as a reminder, our elevator problem was saying all these people have to get to these different floors, but there's only one elevator on this building, and the elevator can only hold 3 people at a time. How do you send the people up the elevator or up in the elevator so that the elevator doesn't have to travel super far and that this doesn't take a whole lot of time, right? So what's the minimum times and stories that you have to travel with this elevator to get everyone where they need to go to? Okay, so hopefully you thought about this, you spent a little bit of time thinking about the best way to get everyone up, and you calculated a final number. Okay, but I want to go through an algorithm that you can follow that will always give you the right solution to this. Okay, so the first step that hopefully most of you realized is it doesn't help to send them up randomly. We need to organize them to be effective. So the first step of this algorithm is to organize each person in order from smallest to largest. Okay? That way you know how to group people effectively so that you can send them up the elevator in an effective way, right? You want to group people that have to go to similar floors in the same ride so that people aren't going on long solo trips up or down the elevator. Okay? After that, a lot of people recognize that. Some people forget this next step, and it's a very important one, is how do I group? Okay? And it really matters that the largest numbers don't get grouped by themselves. So, for example, if you group all these small numbers together, but then this guy that has to go to floor 99, if he's left by himself, then he has to do a solo trip all the way up to floor 99 and no one gets grouped with him. Okay? So how you group matters. So the second step is starting at the largest number, okay, make sure to group people into 3. So that way, the person that has to go all the way up to 71 and all the way to 93, they get to kind of piggyback off the person that's already going all the way up to floor 99 so that they don't have to do these long solo trips. So you want to group the biggest numbers first, then group the smallest numbers. Okay. Lastly, we send them up the elevator, and then there's one more thing we need to think about. Who do we send up first? And it's important because the order that we send them up matters, because on that last trip, they don't have to come back down. The elevator doesn't have to come back down to pick up anyone. Okay. So, for example, this group that has 2 and 8, it'll have to go up 8 floors and then come back down 8 floors, right? Whereas if we send that group first with 99, it'll have to go up 99 floors and then come all the way back down 99 floors. So we don't want to send them first because we'll have this huge long trip where nobody's riding the elevator because we're waiting for it to come back. Okay. So the third key and third step is to realize that we need to send the smallest numbers first. So we group by largest numbers, but we send by smallest numbers. Okay, so we'll send this group, then this group, then this group. And then the last group gets to ride up the elevator, but they don't have to come back down, right? And so we want to send them last because that saves on floors travel. There's not a big long solo trip where nothing's in the elevator. Nobody's in the elevator. Okay? So if we do that with these numbers, okay, then this is what we get. We get 309 floors traveled. Because this group right here, right, their largest number is 8. So they're going to have to travel up 8 floors, come back down 8 floors. Okay? So that's 2 times 8. That's 16 floors traveled. Then this group, their largest number is 35. So they're going to have to go up 35 floors and then go back down 35 floors. So 2 times 35, that's 70 floors. Then this big group, their biggest number is 62. So they'll go up 62 floors. Then the elevator has to go back down 62 floors to pick up the next group, right? So whatever that is. And then the last group goes up 99 floors, but it doesn't have to come back down because there's no one to pick up, okay? And so when you do that calculation, 2 times 8 plus 2 times 35 plus 2 times 62 plus 1 times 99, you get that the minimum number of floors possible is 309, okay? So hopefully you got a number relatively close to that, okay? But again, if you always follow this process in this problem, you will always get the optimal answer. Okay, so that's the key. So even if this sounded like a weird problem and maybe it was a little bit confusing at times, that's okay. What I want you to understand is I don't want you to think of this as a problem by itself, right? These numbers can change. The grouping size can change. Things can change, but if we have a process or a set of steps we follow, we'll always get the answer we want. Okay, that's the point of an algorithm. Okay, so again, right, we need certain calculation steps that we're following so that given any set of numbers in our problem, if we follow those steps, we'll always get the output that we want. Okay, that's the key. So specifically for the elevator problem, I want you to think about what was the input, what are the calculation steps, and what is the output. Okay, well, the input we kind of talked about. It's the numbers of the floors that people need to go to. So even if we had 30 people and they all had different floors than what we mentioned before, that's always our input. The floors they need to travel to and the number of people. But the calculation steps will always solve that problem. That's what we just went through. Sort the group by a number, then group them by the largest, and then send them up by the smallest. Those were the calculation steps we just talked about. Okay, and then the output is hopefully the smallest possible trip, right? The shortest possible trip in the elevator. Okay, so that's the beauty of an algorithm. Okay, again, the nice thing is it can adapt too. So even if there are, n number of people, I put n here meaning you can have any number. If there's 100 people waiting for the elevator, if there's 1,000 people waiting for the elevator, okay, it doesn't matter. Our algorithm will still work. Okay, it has the exact same steps. And even if we change the number of people that the elevator holds, right, it still works. You just group in larger sizes, right, for, you have 100 people waiting in line and the elevator holds 7 people at a time, okay, this still works, okay? No matter what, no matter what this number is, 7 people at a time, 12 people at a time, no matter how many people are in line, it still is going to work as this algorithm, okay? So that's the beauty of algorithms and computer programming. If you set up the algorithm properly, then it will always work, okay? So here is a official definition. You do not have to write algorithms like this, but I just want to make sure we're clear on what an algorithm is. It's not a solution to that particular problem. It's this particular description. Okay, so given a list of people that want to ride the elevator and the floors they need to travel, follow these steps. Okay, sort the people by the floor they want to reach from largest to smallest. Starting at the largest numbers, group people into groups of size M, right? And our example problem was 3. 3 people could fit into the elevator. Or if it's 12 people that fit into the elevator, you just group them into that size, starting from the largest. Okay? Then starting at the smallest numbers, let the people go up the elevator and then have it come back down. And then for the last group, they ride the elevator up, but they don't need to ride the elevator back down, thus saving on floors traveled. Okay. So the output will always be the total floors traveled, or I should say the shortest trip possible, which is 2 times the largest number in each group, except for the last group, which only travels once. Okay. Again, this is very formal. Don't feel like you need to be able to replicate this in your own descriptions. But this algorithm will always be able to solve the elevator problem, no matter the group size, no matter the number of people that are waiting in line, no matter what floors they need to travel. Okay? So, there you go. That is our full solution to the elevator problem. And not just that example, but any elevator problem example. Okay? Let's look at some other algorithms that you might be a little bit more familiar with. Okay? So I want you to think about finding a word in the dictionary. Okay? Nowadays, you just go to Google or something, right, if you need to look up a word. But think back to the old days where you actually had a physical dictionary and you're flipping through those pages to try and find a specific word, right, in alphabetical order. Okay? What you probably did not do is start on the first page, say, oh, the word's not there. Go to the second page. Nope, the word's not there. Go to the third page. Nope, the word's not there. Go to the fourth page. Right? That would take forever. You would never do that. Okay, so without even thinking about it, you probably developed an algorithm, okay, for searching for a word in the dictionary. Okay, so first question is, what is the input? Okay, what are the calculation steps, and what is the output? Well, the input is the word you're trying to find, right? I'm looking for a specific word in the dictionary. That is the word I want to find. Okay. Now let's think about the calculation steps. I'm trying to find what page it's on, okay, which is the output, by the way. So I'm given a certain word, that's my input. What page is it on? That's the output. I'm going to try and find that word in the dictionary. My calculation steps in this case are go to a page, right, kind of open in the middle, and then if that word is past the word I'm looking for, then I'll go to the closer to the beginning. If it's after, or if the word I'm looking for is after the word on the page, I'll go a little bit more towards the end, right? So you kind of follow this process. You don't go one page at a time. You kind of go in the middle. Oh, I went too far. I'll go a little bit more towards the beginning. Oh, now that's a little bit too close, so I'll go in the middle of that one, right? And you kind of do this search of go in the middle, see if it's less or more, okay? And so this is the full algorithm, okay? So again, very formal. Don't feel like you necessarily have to follow these exact wording, but this is the key, okay? So my input is a word in the dictionary. My output is the page that word is on. These are the steps I follow for that to happen, okay? So I flip to a page about halfway through the search area, okay? If your word is on the page, you're done, right? You were really lucky if you happened to open to it, okay? If not, if the word comes before the word on the page, search on the left half of the dictionary, okay? If the word comes after the word on the page, search on the right half of the dictionary, okay? And then you repeat these steps until your answer is found, right? So you kind of get closer and closer and closer to your answer as you switch halfway between, right? And you get narrower and narrower search area until you find the page you're looking for, okay? So again, you probably even need to think about that, but that's an algorithm that you follow, okay? You have certain steps that you follow to get exactly what you want, okay? In fact, this particular algorithm is so common that they call it the binary search algorithm, okay? Computers actually do this when they're trying to find files on your system, okay? We think of computers as being magic and can pull up any file, but they have a big long dictionary of all the files on your computer, and that dictionary is sorted by alphabetically, and so to find a file that they need, they'll actually do this to find certain files, okay? So even computers, especially computers, have to follow algorithms to get what they want, okay? All right, so here's another way you can think about an algorithm. You guys ever see these kind of diagrams or flow charts that are common in a lot of like infograms and things like that on the internet. Okay, that's another way you can think about an algorithm. Given a certain state, right? If that's true, then go this way, or if that's true, go that way, etc. That's what an algorithm is. What do I do given this setup? Oh, I'll do this. If I'm in this setup, I'll do that. Okay. So those flow charts you may see where you make decisions, that's a very common way of visualizing and understanding algorithms. Okay. This one right here is actually for the binary search, right? And so it has, again, very fancy notation of, oh, if my word's before that word, then I'll go this way. If my word's after that word, I'll go that way. Okay. But flow charts are another great way of visualizing algorithms. Okay. So for your homework, we want to practice this process of making algorithms. You can either do it with a flow chart of, given what's happening, go this way, or given what's happening, go that way. Okay. Or you can kind of try and write it a little bit more formally like I did. What's the input? What's the calculation steps? What's the output? Okay. But this is the problem I want you to think about. Okay. So let's think about bringing electricity to a couple of homes in a neighborhood. Okay. You want to figure out the fastest way to get electricity to everybody. So electricity is nice because you just have to have a wire from a spot that already has electricity. Okay. So you don't have to necessarily go in a circle or anything. You just need wires connecting all of these houses. At least one wire connecting all these houses. So if these numbers right here represent the shortest possible path, okay, or shortest distance between this house and that house, what is the shortest set of electrical wires that connects everything? Okay. That's the question you want to think about for your homework and want to do for your homework. Okay. So for example, like this 6 right here, that's a really long distance between these two houses. It's actually faster to go from this house to that house, right? 4 and 1 is less than 6. Okay. So it makes sense to have 2 wires here, and then all 3 of these houses are connected. Okay. So which wires do I need so every house is connected to at least 1 wire, and so that all the houses are connected? Okay. That's your homework. We'll talk about it in the next video. Okay. We'll look at the solution. Okay.